Hi and welcome everybody to the next lecture of the course Evolutionary Dynamics. And in the last couple of lectures, what we had started with was a discussion on evolutionary game theory and how we can visualize evolution in a microbial population when we have two different genotypes competing against each other in a game theoretic framework. But the assumption and we had ended the last lecture by a discussion on stability of these strategies in a game theoretic framework, or in our context of bacterial populations, the stability associated with a particular genotype. But the assumption that we had made in that particular analysis was that the population size was infinite. And that assumption was made when we were discussing and defining an evolutionary stable strategy, an ESS, when we had defined the fitness of a particular mutant which was competing, which had just arisen in a population of strategy A, and the mutant is playing with strategy B. We had said that strategy A, which is the population strategy, is a stable one if its fitness is more than the fitness associated with that of the mutant strategy that has just arisen in the population. And the condition that we had imposed on the wild type or the parent strategy or the parent genotype to be stable was that the fitness at that particular instant, where n-1 individuals are of strategy A and 1 individual is of strategy B, A is said to be a stable strategy if its fitness, if the fitness of an individual belonging to genotype A is more than that of the mutant which has just arisen. And when we did that, we put the frequency associated with the mutant genotype as epsilon, and the next step that we had made in that derivation was that this epsilon is a negligible number, is a very small number, and hence we dropped all terms which contained the factor epsilon in them, and that gave us a result in terms of the elements of the payoff matrix which told us whether strategy A is stable or not. However, the assumption that we can drop the terms with epsilon is based on the fact that population size is very large. But populations may be very large, but it's a fact that populations are always going to be finite. And on top of that, if population sizes are not very large, then the relationship that you get for a strategy A to be an ESS is in terms of the elements of the payoff matrix and also the number of individuals which are there in that environment. So it's an interplay between the elements of payoff matrix and the number of individuals present in the environment that allows you to comment on whether strategy A is an ESS or not. And that's what we are going to do in today's lecture, is look at how does a finite population size, and especially if that finite number is not very large, if the n associated with the environment is very small, how does that dictate the condition whether strategy A is an ESS or not. So that's the goal that we'll be working towards today, analysis of effect of finite small populations on whether strategy A is an ESS or not. So we'll begin our analysis by defining a payoff matrix just in the manner that we've been doing so far. So payoff matrix P is just strategy A and B, or genotypes A and B, and the payoff associated with the row strategy when competing against the column strategy is given by ABCD. This is what we've been doing so far. Now we'll assume that we need to assume a finite population size. So we'll say that the total population size associated with this environment is equal to n, and at any particular instant that we are interested in talking about here, the number of individuals which belong to genotype A or strategy A is equal to I, and that automatically means that number of individuals which belong to genotype B or strategy B is equal to n minus I. And next what we want to do is we want to calculate that what probability does an individual of type A have of meeting another individual of type A? What probability does an individual of genotype A have of meeting another individual of genotype B? And for that, we're just going to make a very simple assumption that the probability of meeting an individual of a particular genotype is just proportional to number of individuals which are present in the environment which belong to that particular environment. So, if of all the other individuals which are present in the environment, half are of genotype A and half are of genotype B, my probability that I will meet someone from genotype A is just equal to half, and this is just in proportional to the number of individuals which are present which belong to a particular genotype. So, for our analysis, since the population size is n and we are talking in the context of what probability does one individual have of meeting another individual of genotype A, then from the context of that particular individual, there are n minus 1 other individuals. So, the total population size from the context of one individual is not n, but there are n minus 1 other individuals that this individual sees. So, we will just put that down, that for each individual there are n minus 1 other individuals in the population. So, for an individual with genotype A, there are I minus 1 individuals with genotype A and there are n minus I individuals with genotype B, right? Because in all there are I individuals with genotype A. So, for an A individual there are only I minus 1 other individuals which have this genotype. Similarly, for an individual with genotype B, there are I individuals with genotype A and n minus I minus 1 individuals with genotype B. And in both these cases, the number of other individuals that are there, both these quantities add up to n minus 1 and n minus 1. Okay. That is to be expected because this takes care of everybody in the population who is not that particular individual. So, now if we have this, the next step is just defining probabilities, that what is the chance that an individual has, that an A type individual or a B type individual has of meeting another A type or a B type individual, and that's done that's going to be done in proportional to the frequency associated with individuals belonging to that particular genotype. So, we'll just extend this number to probabilities now, and we'll say that the probability that an A individual, an individual genotype A interacts or meets an A individual, is this probability is just equal to I minus 1 divided by n minus 1, because of all the other individuals that are present in the environment, which is n minus 1, there are I minus 1 which belong to this particular genotype. And the probability that an A individual interacts with genotype B is just going to be equal to n minus I divided by n minus 1. And similarly, we can define equivalent probabilities for genotype B, and again this is in the context, this is from the context of an individual which belongs to genotype B, and we are going to put down the probabilities associated that this individual sees an individual of genotype A or genotype B. So, just as we did for an A type individual, probability that a B individual interacts with an A type individual is just equal to I divided by n minus 1, and this B type individual, the probability that it interacts with the B type individual is just going to be equal to n minus I minus 1 divided by n minus 1. So we have these probabilities associated with both the genotypes of meeting an individual of type A and type B, and the next thing that we are going to do is calculate the associated payoffs for each of these type of individuals. So what is the average payoff depending on taking into account the likelihood that this individual encounters a genotype A and genotype B at the given instant where the structure of the population is defined by variable I, in the sense that there are I individuals and n minus I B individuals. What is the payoff associated with these two genotypes going to be, given that these are the likelihoods of them meeting individuals of these two genotypes, and given the fact that the payoff matrix has a structure as given. So that payoff again is just an extension of what we had done in the last lecture, except for the fact that now we take into account that population size is finite. So let's put that payoff down, and that's going to be, so expected payoffs for the two strategies or two genotypes is just going to be equal to, let's say payoff for A is equal to f of I, which is just going to be equal to A times I minus 1 divided by n minus 1 plus B times n minus I divided by n minus 1. Okay. So we're calling payoff of A as just A into probability that this A individual meets another A type individual, plus B into probability that this A individual meets a B type individual. And we are using the word f here. This is a representative, this is a variable that we are choosing to represent the expected payoff, and the subscript I here represents, this is the payoff when the population structure is defined by the variable I. When the population is at a stage where there are I A individuals and n minus I B individuals. So we do this, and similarly we get a payoff for B, which we are going to write as G of I. Again, payoff associated, G is just a variable we are using to represent payoff of B, and the subscript I again denotes that this is the payoff which is given when the population structure is defined by the variable I, which is the number of A individuals. And this just comes out to be C into I by n plus D into n minus I minus 1 divided by n minus 1. There's a small mistake here. This is not n, this should be n minus 1, because from the context of this particular individual there are only n minus 1 individuals, n minus 1 other individuals which are present. So this is just, let me just write this again. This is C times I divided by n minus 1 plus D into n minus I minus 1 divided by n minus 1. Okay. All right. So we have these payoffs now. We have payoffs associated with genotype A and genotype B when the population structure is given by this variable I, and this also incorporates the payoff matrix elements A, B, C and D. Now we want to connect this payoff with fitnesses. Now payoff and fitnesses, we've often since the start of this discussion on evolutionary game theory, we've been saying that we've been using payoff and fitness somewhat interchangeably. But what we want to incorporate is that payoff from this particular matrix, this particular difference between genotype A and B could influence their fitnesses, the rate at which they are growing, in a different manner. There might be some phenotypes, there might be some differences between genotype A and B where payoff is very closely linked to fitnesses, but A and B could also have genotypic differences where payoff is not very closely or very strongly dictating the fitness associated with these two genotypes. So, to incorporate this, we want to establish a relationship between payoff and fitness, and we will do that via a tunable factor omega. And the way we do this is, we say that first we realize that the fitness, the rate at which these populations are growing, is equal to some function g of payoff. And we do not know what this function is, but we make an assumption that fitness f of I, this is fitness of genotype A, is just going to be equal to 1 minus omega plus omega into Fi. And Fi is the payoff associated with the population structure and the given payoff matrix as defined in the previous slide. So, this is capital Fi, and what we are saying is that the fitness of A, small fi, is just equal to this, where omega is a parameter associated with this definition. So, let us see what happens when omega is equal to 0. If omega is equal to 0, what you are saying that f of I is equal to 1, and the payoff associated from the fitness payoff associated with the evolutionary game that we are talking about here has actually no impact on the fitness associated with the genotype. So, payoff and fitness in this case are not linked at all, and what we have a case here where we are saying that fitness is independent of payoff. So, this would be a case where if you have two genotypes coexisting in an environment and they are interacting via the payoff matrix as we have defined, then no matter what the return to a particular genotype is from that payoff matrix, that return does not in any way impact the growth rate associated with those two genotypes. So, growth rate, the variable growth rate is independent of the returns that the particular genotype derives from the payoff matrix. That is a case that is represented by omega equals 0. On the other extreme, we can have omega equals 1, which would imply that f of I is equal to capital F of I, because when we plug omega equal to 1, these two will cancel each other, this is just equal to 1. So, we get small fi equal to capital Fi, which implies that fitness is equal to payoff. So, this would be a case where the return that a particular genotype is deriving from the payoff matrix is very strongly related to the fitness or the growth rate associated with that genotype. So, we call omega equal to 1 as the case where there is very strong selection in terms of the payoff matrix that we have defined, and we call the case when omega is equal to 0 as there being no selection, because the returns from the payoff matrix do not in any way dictate what is the growth rate associated with that genotype. So, when we are defining these models, we tune the variable omega between 0 and 1, and that takes us from one extreme where there is no selection in terms of the game being played in terms of the payoff matrix that we have defined, to omega equal to 1, where the payoff the return from the payoff matrix actually very strongly dictates the rate at which these species are going to grow. So, depending on what value of omega we choose between 0 and 1, we get the corresponding growth rates associated with any particular individual genotype. And of course, this is Fi. Similarly, Gi, which is the fitness of B, will be correspondingly defined as 1 minus omega plus omega into Gi, where Gi is the payoff return from the matrix that we defined in the previous slide. This gives us Gi, and when we plug Gi here, that gives me the equivalent growth rate for genotype B. Alright, so omega for any case is just going to be the same value somewhere between 0 and 1 depending on the exact phenotype which is associated, or the exact relationship that is associated in terms of the physiology of the organism when I am looking at strategies A and B, but it is going to be a variable between 0 and 1. Okay. So, now when we have this, suppose we have a population at a structure I where there are I A individuals and n minus I B individuals. Now we want to calculate what is the chance that if we were to apply the Moran model to this process, that the system transitions from state I to I plus 1. And remember, Moran process was discussed earlier in the course, where we said that in each step there are two processes that happen in the Moran process, that you choose an individual for birth and you choose an individual for death. Hence, depending on if you chose an A-type individual for birth, that means the number of A-type individual goes up by 1, and if you end up choosing a B-type individual for death, that means the number of B-type individuals goes down by 1. The consequence being that you move from a state of the system where there are I A individuals and n minus I B individuals, you move to a state where there are I plus 1 A individuals and n minus I minus 1 B-type individuals. So, that is a transition we said, that the system goes from I to I plus 1. So, we do that similar kind of a thing, and the idea being that we want to incorporate population size. N is a variable that is associated with all our fitness definitions here. So, we want to incorporate that effect and calculate this transition probability. So, if we apply that Moran process formula here, and we want to compute Pi to I plus 1. Now, this transition can only happen when you are selecting an A-type individual for birth and B-type individual for death. So, this happens when probability A birth times probability that a B-type individual gets selected for death. And as we have done before, the probability that an A-type individual gets selected for birth is in proportion to the fitness associated with the A genotype, and that fitness we have already seen is equal to f of I. So, and since there are I number of individuals which belong to this genotype, the total fitness associated with A-type individual is I times Fi, and the total fitness with all individuals in the population will just be I times Fi plus n minus I times Gi, where Gi is the fitness of the n minus 1 B-type individuals in the population. And the probability that B gets selected for death is just going to be equal to n minus I divided by n. And the way we had defined this, we had said that it is only the birth processes which are selected weighted in proportion weighted by their fitnesses. The death processes are selected totally randomly without any weight associated with fitness. So, that is the probability that the system transitions from state I to I plus 1. Similarly, we can have another probability that the system transitions from state I to state I minus 1, and that will happen when you select a B individual for birth and an A individual for death. And using the same logic as above, this will happen with the probability n minus I divided by Gi times Gi divided by I times Fi plus n minus I times Gi, and the probability of choosing an A individual for death is just going to be equal to I divided by n. So, our transition probabilities now incorporate n as one of the variables which has come into being, but of course, there are two more transitions, two more events that can happen, that you select an A-type individual for birth and A-type individual for death. So, selecting an A-type individual for birth increases the number of A-type individuals for 1 by 1, and selecting a A-type individual for death decreases the number of A-type individuals for death. Hence, the total number of individuals belonging to A-type remain constant at I, remain the same as the previous step, which is equal to I, And similarly, you can have a B selection of B for birth and B for death, which would also ensure that the structure of the population does not change and it remains at I. And in both these cases, the structure of the population does not change. So, the probability associated with those steps is the transition probability that the system remains from I at state I, and this can simply be written as 1 minus probability that the system transitions from I to I plus 1 minus probability of I to I minus 1. And this comes from the fact that we already know that the three transitions Pi to I plus probability that system changes from I to I plus 1 plus probability that system transitions from I to I minus 1 is equal to 1. Because the way we apply Moran process, these are the only three transitions that are possible with the population. You cannot have any other transition other than these three. Hence, the sum of these probabilities is 1, and I have already computed expressions for these for this probability and this probability. So, the third one can simply be represented as a function of the other two. Okay. Before we go ahead, just a few simple intuitive definitions of PII, applications of PII. We have done this before, but you should just answer these 4 probabilities by pausing the video for maybe 30 seconds and just answer that what are these probabilities. So, I am plugging specific values of I here. We are plugging specific values of I, which is the state at which system starts, and the second value here represents the state at which the system ends after one step of Moran process has been applied. So, again the numbers here should be 1 0 1 0, and because this is true, because let us look at the first one, P00 means what is the transition probability that we start at a state where I is equal to 0, that means there are no A individuals, and end at I equal to 0, which is there is no A individual. Because there were no individuals to begin with and there are no mutations permitted in the Moran model, the probability of this happening is equal to 1, because this means that you are going to pick a B type individual for birth and pick a B type individual for death, and if you do that, this probability is just equal to 0, is equal to 1, and so on and so forth. You can convince yourself of the other 3 as well. So far in this lecture, what we have done is derived an expression of these transition probabilities where the population size n has come into being. What's critical to us, or what we'll be working towards in the next lecture, is that the particular value of I that we are interested in is 1, which represents the physiological case that you have a genotypically identical population where all n individuals are of the same type, and via mutation and a birth and a death process, one mutant has arisen, so that your population structure is now n minus 1 individuals of one type and 1 individual of one particular type. And in this scenario, what we are interested in is that what is the probability that this one individual is going to be able to establish itself and spread through the population and eliminate all other n minus 1 individuals. And specifically, we want to study this relationship in the context of population size, and how does the variable n, the population n size, dictate this probability. Continue with that in our next lecture. Thank you.